In this video, we're going to talk about limits and continuity. So remember back in Calc 1, where you were looking at limits of functions of single variables, you were trying to determine what happens to a function around where the x value gets closer and closer to a. Okay? You can really only, one way to do that is to consider what happens when x is really close to but a little bit less than a, or x is really close to but a little bit greater than a. But those are really the only two directions that you can get closer and closer to a, right? You're on a one-dimensional axis. You can only come in from the left or the right. There's not a lot of different choices that you can get closer and closer to a. However, for a limit of a function of two variables, we no longer have this notion of limit from the left or limit from the right. There are all sorts of different ways that x, y can get closer and closer to a specific point. You've got more latitude because now you're in two dimensions instead of one. So what do I mean by that? Well, here let's say we wanted to get closer and closer to the point 1, 1. Well, one way to do that is hold your x value at 1 and get closer and closer with your y's. That's one way to get closer and closer to the point 1, 1. Another way is to hold your y equal to 1 and get closer and closer to with your x's from left to right. Okay? Or another way is to follow some other types of weird curves. Or maybe not even necessarily so weird, but some other types of curves. Here's one. Why don't I get closer and closer to 1, 1 by staying on the parabola x squared minus 2x plus 2? As long as I stay on there and get closer, and let my x's and y's get closer and closer to 1, I'll get closer and closer to that point. Or if I want to be even weirder, I could use, say, the y equals x plus x minus 1 times sine of 1 over x. That would give me some weird expression here as well. Actually, this should be 1 over x minus 1. There should be an x minus 1 in the denominator here. But regardless, the whole point of this is that I can go by really, really weird paths and get closer and closer to the point, right? It's not just a left or a right idea. Okay? This one bounces infinitely many times, in fact, before it gets to the point 1, 1. All right, so let's look at a specific example here of limit and see if we can evaluate it. So we'll look at the limit as x, y goes to 0, 0 of x cubed plus y cubed over x plus y. One of the ways to try to do this would be using techniques that we did in Calc 1. The numerator factors. And then as long as we don't plug in 0, 0, well, actually, as long as you don't plug in x is the negative of y, this expression is defined, and we can go ahead and cancel those pieces out. We just get x squared plus xy plus y squared, which will give us 0, because I can just plug in at that point. And if we graph this, this is exactly what we get. We get another one of those elliptic paraboloid types of things. It's rotated, but it's the same kind of shape. Here's an example of a limit that exists, and we just evaluated it using techniques that we used back in Calc 1. However, that doesn't always work. So let's look at this one as xy versus 0, 0 of x minus y over x plus y. So one thing that we'll try is just looking at what happens as you come along the axes. See what happens. So if we come along the x-axis, or along y equals 0, we plug 0 in for y. X still has to approach 0, so this changes to a limit as x approaches 0. Since the y's are 0, we just get x over x. And that just is a matter of taking the limit of 1, which gives you 1. Okay? So coming along along the x-axis, the surface is actually equal to 1 the entire time. Let's go along the along the y-axis this time. X would be 0, so those go away. We get negative y over y. In this case, it's just y that's going to 0. And if we calculate that limit, we get negative 1. Notice if these limits don't agree, and just like in Calc 1, if they don't agree, the limit does not exist. What does that look like graphically in a function of two variables? Okay, so this red line here is representing the x-axis, so y equals 0. Notice on the graph here, if I look at the points on the surface right above the x-axis, I've got points that are right there at 1. That's what that curve right there on the screen is. That's the z value for all of those points that are right directly above the x-axis. If I go to the y-axis, which is the green one, this part right here is the line right directly below it. And I see that those are all right at -1. So that's what the surface looks like. Limit as you approach x, as you go 0, 0 along the x-axis, you're at 1. Along the y-axis, you're at -1. So it does not exist. All right, let's do another one here. Limit as xy goes to 0, 0 of xy cubed over x squared plus y to the 6th. All right. Do the same kind of trick. Let's go along the x-axis, put in 0 for y. Notice in that case, we just get 0. Notice though, again in this case, if we put in x equal to 0, go along the y-axis, we still get 0. Now, these agreed this case, but that does not tell us that the limit exists. That's only 2 possible paths, and as we talked about a few slides ago, there are infinitely many paths to get closer and closer to 0, 0. So we might have to try something different. What's the something different we're going to try? Well, let's look down here. Notice if I plug in y cubed for x, I can combine the 2 terms of the denominator. Okay, so that might allow us to do some computations. So let's go along the path x equals y cubed in this case. Okay, so if we plug in the x equals y cubed, we get a y cubed times y cubed on top, a y cubed squared plus a y to the 6th on bottom. And in this case, everything is now in terms of y, so the y just has to go to 0. Change the limit of 2 variables to the limit of 1 variable. We can combine terms and cancel and get a half for our limit. So now we see that different paths give us different limits, so the limit does not exist in this case. I don't know why I put an extra 2 in here. This 2 shouldn't be here. All right, so I guess this is just a typo. It should just be the original function. I mean, it's not that it's false, it's just that the 2 had nothing to do with the problem. All right, let's look at the graph here. So here is, if you can kind of see it in the graph, here is, along this peak, here is the curve x equals y cubed, or y equals the cube root of x, if you will. You can kind of see it here, right? You see this S shape here. And it's a little hard to read on the screen, but you can tell these are decimals along your z-axis, and they really do look like we're getting closer and closer to 0.5 there. The reason, of course, why there is this missing gap in the surface is because we really are getting numbers that are close to 0, and computationally speaking, that's hard for the computer to work with. This is why the surface looks a little goofy. But again, you can see it, right? Here's the curve x equals y cubed, and it gets closer and closer to 0.5 for the outputs. All right, so we've seen a case now of a couple of them where the limit does not exist. Let's look at one where the limit does exist. So let's look at this nasty looking expression. Limit as xy goes to 0, 0 of inverse tangent of x squared plus y squared minus x squared plus y squared over x squared plus y squared quantity cubed. All right, so one of the things that we've learned from way back in chapter 10 is that if we see x squared plus y squared, probably want to start thinking about polar coordinates. All right, so if we go, if xy gets closer and closer to 0, 0, that means that the r coordinate, which is square root of x squared plus y squared, must get closer and closer to 0, and it has to be from the right because this is never negative. So if we can change this to polar coordinates and do our appropriate coordinate conversions, we can change this into a limit of r rather than a limit of x comma y. All right. And this is not quite right. Unfortunately, I should have squareds on these things. Let's just say, for argument's sake, so that I don't have to go back through and reshoot the entire video, let's just pretend like each of these x squareds plus y squareds in the original problem all have radicals over them. Okay? So let's just, if you're writing it in your notes, just put square roots over each of these. Okay? And then each of those will actually be r in that case, rather than r squared. Technically, I should have been putting r squared in each of those places, I really don't want to go back and reshoot the video just because I forgot to put the radical in there. So, like I said, if you're taking notes on this, put square roots over these so that we really do have r there instead of r squared. All right, so now we've changed it to a limit of a function of one variable. We can apply our one variable function limit ideas to this limit, which means L'Hopital's rule in this case, because we really do have 0 over 0. We just try to put in 0 for r. L'Hopital's rule says take derivative of the top over derivative of the bottom. Simplify. And so I got a common denominator here and simplified. Cancel your r squareds and take your limit and get negative a third. So again, the reason why there's this weird spike in here in the surface is because, again, if I actually graph the surface, it's trying to put something that's really close to 0 in the denominator, and it has issues with it. But you can see here, just from the graph, here's about 0.3, and the mirror image down here at negative 0.3. So you really do see that the surface, no matter which way you come in from, it does get closer and closer to that negative 1/3 idea. All right, let's just talk briefly about continuity. So much like the definition of continuity back in Calc 1, if we want the limit, if the function is continuous, if the limit is equal to the function value, we can evaluate the limit by direct substitution. Okay? Of course, it has to be defined at that point as well. We say it's continuous in an entire set. If it's continuous at every point in the set, that's not any different than what we do for continuity on the interval for a function of one variable. And the reason why I'm not saying much about this is because for our purposes, we're going to be worried about functions that are what's called continuous on their domains. And all that means is that as long as you can plug the number into the function, or in this case the tuple into the function's continuous there. Okay. So there may be places where the function is discontinuous, but the only places at which that can occur is if the function is undefined there. So we don't have to worry about the function being defined but not being continuous at a point, unless you've got some sort of a piecewise defined function, and we're not going to do a lot with that. So for our purposes, as far as we're concerned, when you're asked questions about continuity of a function, you're really just being asked questions about the domain of that function.